This slide introduces Section 4 of our program, Material Requirements Planning, or MRP. In Chapter 4.1, we'll understand what MRP is, why organizations use it, and how it helps plan materials efficiently based on demand, inventory levels, and production schedules. The goal is to ensure the right materials are available at the right time to support smooth operations. This slide explains what MRP is, a computerized system that calculates the materials needed for production. The key idea is ensuring the right materials are available at the right time to meet the master production schedule. MRP works using three core inputs: the MPS, the bill of materials, and inventory records. Together, these help plan material requirements accurately and prevent shortages or delays. This slide highlights the main outputs of an MRP system. It tells us what orders to release, when to reschedule items, and flags exceptions when something needs attention. The example shows how MRP converts an MPS requirement like 100 bicycles needing 200 tires into an exact material plan based on lead time and current inventory. This slide covers the key objectives of MRP: ensuring material availability, reducing excess inventory, improving delivery performance, and giving accurate scheduling data. The mini case shows how Bosch used MRP to cut inventory by 20% and boost order fulfillment to 98%, demonstrating the real-world impact of effective MRP. This slide explains the bill of material, or BOM, which is a detailed, hierarchical list of all components needed to build a product. Using a bicycle example, Level 0 is the final product, Level 1 includes major assemblies like frame and wheels, and Level 2 breaks them further into parts like tires, rims, and nuts, bolts. BOM helps understand structure and plan material requirements accurately. This slide covers different types of BOMs. Single level shows only immediate components, while multi-level includes all sub-assemblies. Modular BOMs support configurable products, and phantom BOMs are used for temporary assemblies. The example of a car engine shows how MRP expands a multi-level BOM with thousands of parts to calculate total material requirements. This slide explains why BOM accuracy is critical. Errors can cause stockouts, excess inventory, wrong orders, and scheduling delays. To avoid this, organizations must control BOM revisions, ensure collaboration between engineering and planning, and conduct regular audits. The Whirlpool case shows how a centralized BOM reduced design issues and cut part duplication by 12%. This slide explains how the MRP system works through the MRP explosion process. MRP takes the master production schedule MPS and breaks down the bill of materials BOM to calculate material needs. It checks inventory levels, scheduled receipts, and lead times to decide when orders should be released. The four main steps are: netting, calculate net requirements by subtracting on-hand inventory and receipts from gross needs. Lot sizing, decide the quantity to order EOQ, L for L, etc. Time phasing, apply lead times to determine order release dates. BOM explosion, break requirements down to lower. This slide shows a simple MRP calculation example for wheel and tire. For each item, we look at lead time, gross requirement, on-hand inventory, and net requirement. Wheel, 200 needed, 20 on-hand, net requirement 180. With 1 week lead time, order is released in week 1. Tire, for 100 needed, 100 on-hand, net requirement 300. With 1 week lead time, order is released in week 0. This demonstrates how MRP uses inventory and lead times to determine when to place orders. This slide explains the exception messages generated by MRP, such as expediting or deferring orders, canceling planned orders, and alerts for shortages. These messages help planners respond quickly to changes in demand or supply. The mini case study shows that Caterpillar reduced planner intervention time by 35% after automating bomb explosion and exception handling, proving how automation improves efficiency. This slide covers lead time management and operations. Lead time is the total time from placing an order to receiving it. There are two main types. Manufacturing lead time includes processing, setup, movement, and queue time. Procurement lead time includes supplier processing, transportation, and receiving time. Effective lead time management helps improve planning, inventory control, and responsiveness. This slide explains the main lot sizing methods used in inventory management. L4L orders exactly what's needed, minimizes inventory but increases setups. EOQ balances setup and holding costs best for steady demand. FOQ uses a fixed batch size, making production planning simple. POQ groups orders across several periods, useful for time-phased requirements. Example shows how EOQ is calculated based on demand, setup cost, and holding cost. Safety stock is extra inventory kept to protect against demand or supply uncertainty. MRP systems should plan safety stock separately to ensure service level targets are met. Example, Philips applied statistical safety stock modeling and cut inventory by 15% while still achieving a 98% fill rate. This slide compares the two MRP processing types, regenerative and net change. Regenerative MRP recalculates everything from scratch, best for simpler systems with scheduled, for example, weekly updates. Net change MRP updates only the items affected by changes, ideal for real-time, complex environments. Example, regenerative runs weekly, while net change updates instantly when new orders arrive. MRPT expands traditional MRP by including labor, machines, finance, and capacity, making it a full integrated planning system. Key features include closed-loop feedback and integration with finance, HR, and engineering. It forms the foundation of modern ERP systems like SAP and Oracle. Case example: GE upgraded to MRP2 to connect production and finance, improving planning accuracy and visibility across plants. This slide introduces MRP challenges when comparing regenerative versus net change MRP. Key issues include data accuracy, system nervousness from frequent changes, heavy reliance on forecasts, and the lack of capacity feedback, which is later addressed in MRP2. The illustration highlights the practical impact of these challenges in inventory and shelf stocking operations.